Okay, we have just introduced that integrals, the definite integral, indefinite integral, and now we go to chapter 5.4, and then we will look for all kind of properties of those definite integrals. And we will see all kinds of things, and some of them you will say, oh yes, that I could also have seen. Okay. Um, Now, first of all, I go just I take feeling free of chapter 5.4, and I go along that, and you see what we have. If you have a definite integral from a to a of that function fx dx, then you get 0 out of it. The length of your integration domain is 0, and so your integral will also be 0. If you have an integral from a to b, and you take and you reverse the order of integration, so you go from b to a, then you get a minus sign before that integral. So be careful and see you that the boundaries are changed, from the left side from A to B, and from the other one from B to A. Further on, if you have several functions to integrate and you want to have the integral to calculate the definite integral, you can calculate them from um, them separately, and if they are also uh, if they are also multiplied by some constant, you can put that constant outside the integral, so you get the integral from a to b of fx dx, and you get b times the integral from a to b, and that is the case if a and b are constant. So they don't depend on x, but there are constants. And I assume if I use those functions, that those functions are integral, that the integral exists, that you can integrate them. So that I assume that is always the case. And okay. Now further on, I have already a little bit used, but okay. If you have some integral from a to b, from let's see, from a to b fx dx, and you integrate from b to c, then you may also directly go from a to c, and that is no problem. And if you know, sometimes you want to get bounds for integrals. If you know that you have a function which is greater or equal to your function you are busy with, so that if your f is less or equal some function g of x, and this for x less or equal to b and greater or equal to a, if that is the case, then that integral from a to b on the left hand side will be less or equal than the integral from a to b from the g dx. So you see here, that your function f is less or equal to g, and you see that you have the same for your integral. F, g, and here your f, and there your g. No problems. Very often maybe you cannot integrate, or it is too difficult or something, and then you are only interested in some bound of your integral that you have just that you know from it is less or equal to something. Now, if your a is in this case less or equal to b, and let that be always, if you don't, if you have this integral with that absolute values around it, you can also put that absolute values inside the integral, so you get less or equal the integral from a to b, and then the absolute value of fx dx. This is of importance that the a is less or equal to b. That is of importance because of the fact that if you change the order of integration, you get a minus sign in your and on the left hand side you have the absolute value, so that's a positive value, and that has always to be less or equal to some positive and not to some negative value. Then we are not going well. Then we have problems. Now and then, what can we do further on? If your function f you are integrating on some symmetric interval around 0. So here you have your interval AB symmetric around 0, and your function f is an odd function. And with odd, that means that the value of minus x is minus the f of x. If that is the case, then you have a little bit this idea. Then you have that the integral from minus a to a of that function will become equal to 0. So that is, so if your f is odd, and you have your interval, look to your interval, that is a symmetric interval around 0, and if your f is odd, you see that your integral will be equal to 0. Now, and look to it, you see on the, in this case here, on the left hand side your function is negative, on the right hand side your function is positive, and they behave almost the same, only the only difference is that minus sign. So if you add those things together, you will get 0 out of it. On the left hand side you get something negative, on the right hand side something positive. Now, and adding them together will give you 0. Now, if f is even, so the f of minus x is the f of x. Yeah, you cannot do so. You cannot give really some value directly, but then your integral from minus a to a fx dx is 2 times the integral from 0 to a. So you can write your integral a little bit else, but not much. You cannot, I cannot give you some value or so. With an odd function, you can say there comes 0 out of it, no problem. Then the only thing here, you can take 2 times the integral on the right hand side or something like that. And yeah, if I always have some. Sorry, I have to stay. I have always in mind those pictures, those graphs, and then your function is f is even. Now then you have something like this, like some, for instance, x squared or something like that, and then you see that the area beneath this graph on the left hand side will be equal to the area on the right hand side. So you can, so if you take 2 times this area on the right hand side, you will get the integral of the whole function. So the areas will be the same. But be careful again. I I speak to you about areas, but maybe the function can also be negative, and so then you have not you cannot speak about an area anymore because you are speaking about negative values. Um, no, just some examples about uh, how you can do such integrals. Uh, and then, for instance, if you have some integral, somebody asks you to calculate the integral from -2 to 2 of the function 2 plus 5 times x dx. Now, um, maybe it's yeah. But what do we see then? Look through that. What you have to do there, and what do you see here? Here you see the function x, and if your function x is an odd function, you have your interval symmetric around the origin, and so you can directly say to the people that you have there here you get the integral from -2 to 2 times dx. The integral about that odd function will become 0, and we have this here. Now, and what do we see here? Here we have a constant function. This is for every value between -2 and 2 is the function 2. Now the length of your interval is 4, and so you have 2 times 4, and you get 8 out of it. No problem. And we have not worked with primitive functions, so we have not searched for such a capital F function or so. No, we have here just looked to that function, and we looked from how what kind of areas do we calculate, and can we directly write the solution or not. Now, um, also some integral like from 0 to 3 2 plus x dx. Now, what can we do? Then we can also make some graph of that function you were integrating. You have to integrate, so you have the interval from 0 to b, that's the domain. If you fill in x is 0, you get 2 out of that function you have to integrate, and further on you have the function x. So this is the graph of your function you have to integrate. This is your little f, and here you see the graph of it. And now if you now have to integrate to calculate that integral, now what can you do? You can cut it into two pieces in certain sense. You have here the rectangle, and um, and here we have a square of no, also a rectangle, but then half of it. So this one, you will the area of it will be the length of that rectangle is 3, and the height is 2, so you get 6 out of it. And here, this rectangle here, or not, that's a triangle, but it is the half of a rectangle. You get 3 times 3 divided by 2, and you have just the half of a square. Now, and then you can add those values together, and you get your integral. So that integral, that e, the value you have to integrate, just become 6 plus 9 divided by 2, and you get some value out of it. and then you can make one expression of it, 21 divided by 2. Okay, and then another one. Now that will be in certain sense difficult to search for some primitive function. That will be really difficult in this case. But look to what what is staying there. What kind of a figure do you have? Now you have now here this one, and that graph, that is y is equal to the square root of 9 minus x squared. Now, and what do we then have? This is a part of a circle. And you see, if you take y squared and you take the right hand side, you also take the square of it, you get 9 minus x squared, and you see x squared plus y squared is 9, and so you see the midpoint of that circle is 0, 0, and the radius is equal to 3, the square root of 9. Now, and if you now want to have if there's asked to you to calculate the area beneath this graph, it is just the area of a circle, but then divided by 2. So we have here pi times r squared, and then we have to divide by 2. We have a half circle. And here you have that integral. This will be the value of your integral. So, and that integral will then be the integral from minus 3 to 3, and then you have that square root there, dx. So the area of half of a circle here, the PR squared is the area of a whole circle. Here you have a half a circle, so you divide the area by 2. Now, and in this way you can calculate a lot of integrals. Look how they behave. The function you have to look how they behave, and maybe you can do something with it. Okay. And now I want to go to some other parts. Yeah, what did we do? This looks very much like some other theorem we have already used for continuous functions. But here the mean value theorem for integrals. Now, if you know your f is continuous, and you are on some interval ab, so continuous on the interval ab, and and yeah, I don't know, but you 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 want to give somebody some idea about what this value can be, what that integral, what that area can, what you can get out of it. Now, then this integral is equal to some function in some c. That c will lie between a and b, and then times the length of your interval, and then we assume that we have assumed that b is greater than a, and so you have this one here. So there is some c with c between a and b, such that that integral becomes equal to this value here. That's always the case. So you can give some idea, or you have an idea about between what values the integral will become. And, and if you have some to make, you can make some graph of it, some idea. You have your interval AB, you have your x-axis, your y-axis, and you have here some function f, that is the function you integrate. Now, and what is the case? There will be some c. I don't know if this really is here the case, but maybe here you have your c, and then this area here you can put into there. And then you see that your integral, if you integrate from a to b, it becomes equal to the area of the length of that interval AB times the value in C. So you can put that into there, and you have just the integral you want to calculate is just the value in the f of c times the length of your interval. And so you can also speak about the mean value of your integral, your average value, or the average value of a function. That you can also speak about, and that looks in certain sense very much on this theorem, because if you there you see that look to that your f of c becomes equal to 1 divided by b minus a times that integral from a to b fx dx. And so, but then they put this away. They put this away by yes, I want to put away, and I make some average value of it. So I say to the people that oh, and now I'm going wrong. That I don't like what I'm doing now, but I don't know how to. And this is your average value. So this is the average value of f. So if you calculate the integral from a to b of your function f, and you divide it by the length of your interval where you are grading about, you get the average value of a function. Okay. So mean value of the that is of importance. so that you can write your integral with a value f of c out of it, and that c will lie between a and b, that c exists. That's of importance. And then you have the mean value, that is just this integral divided by b minus a, that is just the average value of your function. Now, and what can we do more? Now, maybe f not continuous everywhere. And that is of importance, so not continuous everywhere, but it consists out of piecewise continuous functions. Now, if that is the case, and you have to integrate, then you can make a summation of your functions. So, example. So you have here your interval a, b, the x-axis, the y-axis, and your function is piecewise continuous, so that means there are points where you don't know what the value will be. And let me assume that this value is known, that the value is known. And so you make jumps, but if you now, if your f is this one here, and so you have f1, f2, and f3, then the integral of your function so the integral over that over the interval ab of this one here. Now what can you do? You can cut that integral into pieces, and you have the integral of f1 plus the integral of f2 plus the integral of f3 dx. So you can just cut it into pieces and then add those integrals together. Now I'm not, it is not nice written here, but well, yeah, what can we do here? What can you do with it? You can make C1 and C2, and so if you really want to write it in a very nice way, you get some integral from a to C1 f1 x dx plus integral from C1 to C2 f2 x dx, and you have the integral from C2 to b, and then you have f3x dx. So this is written in a nicer form, and then you have your x variables you have given here, and you have given also your bounds of your integrals. You have given them in a nice way, and it's maybe a little better than what I've just written, the line above that you don't know. But it goes about the fact that if your f is piecewise continuous and you want to integrate it, you can integrate all those pieces separately, and then it will give you the value which is asked to calculate. So new in this case is piecewise continuous. So on on certain parts of your interval AB, there are defined continuous functions, and this is your f, and that you want to integrate, and then you can integrate those pieces separately of each other. Now, and uh, chapter 5.5, yes, that will become a more a more difficult chapter, I think, because you have really to calculate those antiderivatives. Now, and let's see how it goes in the next lecture.